root. So we have our Quiver our Q, and so Q0 vertices, and so by definition we have the quadratic form Q of x. So this is the quadratic form of the Quiver, and so let's put forward the following definition. So we say that we have x with an element in z greater or equal to 0 to not. So x is a root. If u of x is either 1, so this is called real root, or q of x is 0, and this is imaginary root. Okay, so this is our definition, and so let's formulate several properties. So maybe one couple of examples so we can just have it in mind. So if, say, Q is an, just equioriented an, and then we can have x to be just well, e sub I plus e j. So let me recall that so in general, EI is for I in Q naught. Just the how to say, so this is the vector such that EIJ is delta IJ for IJ being vertices of Q. Okay, so this is a vector whose entries are 1 and 0, and 1 at a single place I. So, well, if we take for an x to be EI plus EJ, then Q of x is just n times 1 minus n minus 1 times 1. So this is exactly 1. So because we have n, oops, it's not n, yes, sorry. So this is j minus I plus 1 times 1. So this is the number of non-zero entries we have. And then we subtract j minus I times 1. This is the number of edges we have in this one. Okay. And maybe one more example is u being delta n. So this is the cycle on n vertices, and for such a cycle we can take delta to be just e1 plus so on plus en. So just a vector having 1 at each vertex. So this is the cycle on n vertices. Then what is Q of delta? Can you tell me?
0?
It is, yeah. 0 because this is n minus n, right? So n vertices, while those each vertex contribute 1, and we have n edges, each edge contributes -1, so this is 0. Okay, so let us formulate the following lemma. which has several statements inside. So the first statement is that EI is always a root. For any quiver. So part B is that if alpha is a root, or maybe to make it simpler, let me introduce a notation. So notation. So we say that phi is the set of roots. And so we also have the notion of positive root and negative root. So we say that we have phi plus inside phi and phi minus inside phi. And then this is this set of roots of the form A1, E1 plus AN, EN, where all AI are non-negative. And these guys are AI, A1, E1 plus AN, EN, where AIs are non-positive. Okay, so in principle, so far we don't know whether each root is positive or negative. We'll show that in some cases, but these are just some subsets in the set of roots. Okay, so if alpha is the root, then minus alpha is also a root. And then part C says that so let me see how better put it. So let's say that let's consider the special case. So assume that U is positive semi-definite and alpha is in phi, alpha is not delta. So recall that in the positive semi-definite case, so we have the kernel of our form, and so this kernel is denoted by delta. So let us take a root which is not equal to this delta. Okay, so then the claim is that alpha minus delta is also a root. And then finally, the last claim is that if U is positive semi-definite, or just positive definite, then phi is just the union of phi plus and phi minus. So you see, this is the kind of strong claim saying that any root is either positive or negative. So I think those of you who passed some course on simple Lie algebras, so then you somehow seen such a situation. So I mean, those roots also show up in the Lie theory, and well, we are used to the claim that any root is either positive or negative. And the statement is that the situation is very parallel to that we've seen in the Lie algebra settings. In particular, any root is positive or negative, but not for all quivers, only for an I subclass. Okay, so let us give a proof.
Sorry, may I ask?
Yeah. The roots here somehow corresponds to roots of like the maximal roots of a representation of a Lie algebra.
Well, I mean, The correspondence is as follows. So we'll elaborate on it more, but in short, the claim is as follows. So if you have a Dynkin Quiver, well, of type AD, then there is a Lie algebra which corresponds to this Dynkin Quiver. For example, if the quiver is of type A, then the corresponding Lie algebra is just SLN, and if the quiver is of type D, then the corresponding Lie algebra is SOK, where K is an even number. And then those Lie algebras, they have roots. So they enter the structure of the Lie algebra. So these roots are exactly the roots we have here. So to make it precise, so those EI, which we have in part A of the lemma, they correspond to simple roots of the Lie algebra. And any other root is expressed in terms of these EIs as a linear combination with either positive or negative coefficient. So this is, in short, the correspondence, but we'll discuss this in more details. Does this make sense?
Yeah.
Good. Andrei, did you want to ask something?
Okay, well, delta in C is any imaginary root or
Yes.
or what?
Yeah, actually,
Okay.
we've seen that there is one basic imaginary root, right? So there's a kernel of the form, and this kernel is one-dimensional and is spanned by something, and this delta is this something.
We work in case of Dynkin and the Euclidean quivers, or
so you see, in type C, we assume that Q is positive semi-definite, and we've shown last time that this is the case where the Q is Euclidean.
I thought. Okay, yes, it's true. Thank you.
Okay.
Sorry, I want to ask
Sure.
what's our quiver in this lemma?
Well, if we do part A and part B, we have no assumption on the quiver. And in part C, we assume that Q is Euclidean. So Q is positive semi-definite. And the same assumption is used in part D.
Okay, thank you.
Welcome. So let us give a proof. So actually part A is evident. So can somebody say why?
You can compute.
Alex, please go ahead.
So EI is just the simple representation, right? So we just have
EI is not a representation.
Dimension.
EI is a vector, right? So EI is written here. Yeah. So this is our EI. Okay. So why this EI is a root? So this is just a vector having one entry unit and other entries being zero.
So in the quadratic form, we just have xi squared, and
Yeah.
that I is the only term that's not zero.
Yeah. So this is clear. What about part B? Is it clear as well?
Yeah, if we substitute xi and xj by minus xi and minus xj, then
Right. So there's nothing to prove here. So let us show part C. So what do we know? So we want to compute Q of alpha minus delta, right? So what is that? Let us write Q of alpha. Okay, maybe I just write So let us write the scalar product of alpha and say delta, or let's put minus delta. So what is this scalar product? Can you tell me? Just by definition. How this is the form, the quadratic, the bilinear form of the quiver, how it was defined, do you remember?
Q of their sum minus Q of alpha minus delta minus Q of alpha minus Q of delta minus delta.
Okay.
Yeah, minus delta, right?
Sorry?
That's minus delta.
Yeah, but Q of minus delta is Q of delta because it's quadratic form, yeah?
Ah,
Okay, so what do we know about this term?
it's not negative.
Well, we know actually even more. So you remember delta is the kernel of our form.
But is this kernel or of our form, or is this imaginary root?
No, delta is just the not something, but this is just the kernel of our form. Okay, so maybe I should put it here. So Q is positive semi-definite and delta is the...
But maybe it is the same in case of positive semi-definite cases, which so in Euclidean case, we have one-dimensional kernel of Q, and any imaginary root should be like to this.
Yeah, but let's just stress that this is some very concrete thing. Yeah, so this is not something, but this is just the kernel of the form. You remember last time we just wrote down the coordinates of these deltas for each Euclidean quiver. Yeah, for example, for type A, these are 1, 1, 1, 1, 1 everywhere, and otherwise we just put what we need. Yeah?
And we argued that it's unique or something.
Well, I mean, the kernel is one-dimensional, right? So it means that any other element in the kernel is proportional to this one. So this is 0, and this is 0 as well. So therefore, Q of alpha minus delta is just Q of alpha. Okay. So therefore, so in part C, we wanted to prove that alpha and alpha minus delta are roots together, and this is the proof. And now the last part is to show that any root is either positive or negative. So for that, let us take a root alpha. And let us write down alpha as a linear combination of AI, EI, I from Q0. Okay, so, well, this is a vector and therefore it can be written in coordinates, and these AIs are coordinates of our vector. And so, of course, there might be some positive and negative numbers here. Well, our goal is to show that they are either all positive or either all negatives, right? But in principle, this alpha, so let us just write alpha as beta plus gamma, where beta is the sum for all I, such that AI is positive, AI, EI, and gamma is the sum over all I such that AI is negative. Okay. So just separate positive entries from the negative ones. And for just simplicity, for convenience, let us write beta to be the sum beta I ei overall I, and gamma to be the sum gamma I ei also for I. So what's written here? I just want to use kind of uniform notation for the coordinates of beta and for coordinates of gamma. So let's see. So what do we know about beta I and gamma j? So, well, actually, I want to say something about the scalar product of beta and gamma. So can you tell me, what do we know about that? So maybe I need some estimate or whatever. So is there something we can a priori say about the scalar product of beta and gamma?
Maybe it should be less than 0, but okay.
Why?
I suppose we should write it more explicitly using using fact that components of beta are positive and components of gamma are negative.
Yes.
Then products are negative, but there is some it is a bit not evident how products between EIs work.
Okay, let's write it
It is
then.
not just yes.
So this equals to the sum beta I gamma I minus sum beta I gamma j and ij, right? Okay. So what do we know about this guy?
This is negative because
No,
just because
I claim that we know much more, actually.
Maybe it is 0,
It is. Why?
because when beta I is non-zero, gamma I is 0, and vice versa.
Yes, so because beta i's, they are kind of those, they can be non-zero only if the corresponding ai is positive. And in that case, gamma is 0. So this is just 0. And as Andrei said, this is always less than or equal to 0, right? So actually, we conclude that this is greater than or equal to 0, right? So now let's write it in terms of Q. So beta gamma is Q of beta plus gamma minus Q of beta minus Q of gamma. And let's use that this is greater than or equal to 0. And then we conclude that actually beta plus gamma is alpha, just by the very definition. So Q of alpha greater than or equal to Q of beta plus Q of gamma. So now let's consider two cases. So the first case is that alpha is imaginary root. So then we know that Q of alpha is 0. And therefore, well, what can we say about Q of beta and Q of gamma?
these are also zeros
Yes. Why?
because Q of beta and Q of gamma, because Q is positive semi-definite, and
Absolutely.
then we have sum of numbers which are.
Absolutely. And I claim that this is a contradiction. Can you explain why? So just let's recall, what do we know about, so if Q of beta is 0, then what do we know about this? You remember we had lemma claiming that this is proportional to, so there is only one, yes, vector up to a constant such that Q of this vector is 0. So then is it possible that the condition we have? So I'm claiming that it's contradiction, but can you explain why? So I mean, it's not a contradiction, but what should be the conclusion?
That they're both zero.
Why?
Because it was argued that they cannot have non-zero edges in the same places. But if they're proportional to each other,
Yes.
then they must be zero.
One of them should be 0. So you see,
One of them.
so just the claim is then it means that we conclude that either beta is 0 or gamma is 0. So because they can't have non-zero numbers at the same place, yes.
But why couldn't this happen?
Because what couldn't happen?
That they have non-zero numbers in the same places.
So you see, if Q of beta is Q of gamma and is 0, this means that both are proportional to delta, yes?
Yeah. But why?
But
could they not
delta,
have,
delta has no zeros. You remember that
yes.
actually we've seen it in examples, but we also proved it in general that delta can have no zeros.
Because then it could be more than one dimensional. But why could beta and gamma not have non-zeros in the same places?
Yeah, so just let me repeat the logic. So we know that Q of beta is Q of gamma is 0, yes? So then we conclude from this that beta is constant times delta and gamma is constant time delta, yeah? So assume that both constants are non-zero. Then this means that you remember that delta has no zeros, no zero coordinates at all. So it means that both delta and gamma have no zero coordinates at all. But we decided that beta and gamma cannot have common non-zero coordinates. Okay? So now let's work out the second case. So if alpha is real, so this means that Q of alpha is 1. So we argue the same way, and so we obtain that 1 is Q of beta plus Q of gamma. So what is wrong with this situation? Or maybe not wrong, but how to show that in this situation also either beta or gamma is 0. So what do we know about beta and gamma, Q of beta and Q of gamma in this situation? So if their sum were 0, then we just concluded that they both are zeros, but the sum is 1. How is possible?
one is equal to 1, the other is equal to 0.
Right, right. So we conclude that there are two possibilities. So either u of beta is 1, u of gamma is 0, or u of beta is 0, u of gamma is 1. And so how do we proceed?
But it seems like it's okay, because in this case, to say in first case gamma is proportional to delta, and we know that if we add to beta or substitute from beta some number of deltas, we still will have root.
Yeah, but you
right?
see,
Or
if gamma is proportional to delta, this means that gamma I is non-zero for any I. Okay?
then beta is 0. Okay.
Yeah, yeah.
Right.
And and here we have beta is constant time delta, and therefore sorry. Okay, so let's derive a kind of nice corollary from that. So assume that Q is Dinkin. Then we conclude that there is only finitely many roots. And actually the proof is quite simple. So let's extend Q to Q tilde. So this is the corresponding Euclidean one vertex extension of Q, and let delta be the kernel of the form for Q. Now we know that in particular let us assume that delta is the sum AI EI with all EI being positive. Yeah. So this is the generator with all positive coordinates. This is exactly the one we wrote on the picture last time. So then now for alpha in phi, say phi plus of Q, we have the corresponding root in phi plus of Q tilde, which we denote by the same letter. Also by phi. Is it clear that the roots of Q are embedded into the roots of Q tilde? So just take the one extra coordinate to be 0. Okay. So we add one vertex and then we just put new coordinate to be 0. Okay. So then let us write alpha minus delta. So what do we know about this thing?
It is still a root.
Yes, first of all, it's root. And we know that since the form for Q tilde is positive semi-definite, therefore every root is either positive or negative. What about this root? Is it positive or negative? So we take our alpha. So recall that once again that alpha is just the trivial extension of a root for Q to the root of Q tilde. And we subtract delta and we wonder whether this root positive or negative. So remember that we know a priori that any root is either positive or negative. So there can't be mixture.
I suppose it should be still positive
Why?
because subtraction of delta doesn't change scalar products with EIs. Okay, how to say? Then it shouldn't change. Maybe some decomposition by EIs modulo this delta somehow. Okay, sorry, I can't say more exactly.
But if we take the scalar product with just EI and the new vertex, then shouldn't it be negative because we just have it with delta?
Actually, I claim that this root is negative. And there is very, very kind of naive reason for that.
Like we could take the new vector n plus 1, the one with just 1 in the new vertex that we've added.
Yeah.
And when we take the scalar product with alpha minus delta, we just get.
But why do you need a scalar product? So just let's recall, what does it mean that a root is positive or negative? So just by definition, what does this mean?
Okay, it has one negative component.
Yeah, just by the very construction. Yes, so
along additional vertex, it is -1.
yeah, yeah. So in this one extra vertex we've added to get Q tilde, alpha has no coordinate at all. Yes, this was our extension, and delta is positive everywhere, in particular in this new coordinate as well. So this is in 5 minus. Yeah, but then of Q tilde, but then we conclude that all coordinates, all coordinates of alpha, they have to be no larger than the coordinates of delta. Yes, so if we write alpha to be the sum alpha I EI, we conclude that alpha I is less than or equal than AI. And recall that AI are components of delta. So therefore, the number of positive roots for Q is at most product of AIs. Well, maybe plus 1. Okay. Good. So let me give you an example. So example for if Q is AN, then delta is just the sum of EIs for all I. Yes. So all the coordinates are 1. And therefore, for each alpha from 5 plus of Q, the coordinates of alpha are at most 1. And actually, we know that just by concrete computation, but this is just one more reason for that. Okay. Good. So now we are ready to prove one of the central theorems of the course. So this is the Gabriel's theorem. And the claim is as follows. So first of all, Q has finitely many indecomposable representations if and only if Q is Dynkin. And the second thing, the second claim is that if Q is Dynkin, then the dimensions of the indecomposable representations are positive roots. So the number of indecomposable representations is the number of positive roots, and moreover, the dimensions are exactly the well, a dimension of representation is a collection of dimensions, right? And collection of numbers, and these are exactly positive roots. So remember, for example, in type A, if you have equioriented type A, then all indecomposable representations are kind of segments. Yes, so you start somewhere and then you take all one-dimensionals and you somehow stop someplace. And the roots are also this form. So they have 1, 1, 1, 1, starting from somewhere and up to somewhere. Okay. So let us prove it. So let's first start with the simple part. So assume Q is not Dynkin. Then the claim is then it has infinitely many indecomposable representations. So do you remember why? So actually we've shown that already, but can somebody tell us the reason, just briefly?
Because quadratic form is not positive definite.
That's right. That's right. So we've seen that it's not positive definite, and then the corresponding representation space has more than one open orbit, right? More than one orbit of maximal dimension, right? So this is the case. But now let us now assume Q is Dynkin. So then we are to show that the map psi sending indecomposable representations of Q to positive roots of Q is a bijection. So then, first of all, this would imply 2, yes, because we want to say that the dimensions of, yeah, maybe I should write, well, sorry, so maybe I'm too fast. So the map psi from indecomposable of Q to Z greater or equal 0 Q naught, sending M to the dimension of M. So we want to show that this map has phi plus of Q as an image, and is a bijection between int Q and phi plus of Q. Okay, so once again, so we have the map psi, which just sends any representation to its dimension vector, and then we just take only indecomposable representations, and we somehow look at what's happening in this situation. And the claim is that, first of all, the image is a root. Well, sorry, for an indecomposable representation, the image is a root, and any root can be obtained in this form. So, well, this would give us the second claim of the theorem. Why does it give us the first claim? So assume that we are able to show the properties of power of psi. So we are able to show that psi, the image of psi, is exactly the set of roots, and that this is a bijection between the set of indecomposable representations and the set of roots. So why this would imply part 1?
We proved that for Dinkin diagram there is only point remaining roots.
Right. Okay. So we already know that for Dinkin Quiver, the number of roots is finite. Therefore, if we know that the number of roots is the number of indecomposable representations, then we are done. Okay. So, let us start. So first, what do we prove first? So first of all, first part, let us show that the image of psi sits in the set of positive roots of Q. Okay. So for that, we need to take our M, so let M be an indecomposable representation. So indecomposable representation. So do you remember what is, so we need to show that Q of M is 1. Yes. Can we express, oops, sorry, we can't say Q of M, yes? we can say Q of dimension. So do you remember how to express Q of dimension M in terms of M itself? So we have M, which is a representation, and then we have its dimension vector, and then we can compute our quadratic form on this dimension vector. But we had also had a formula which expresses the value of Q in terms of some properties of M. Do you remember what is that?
It's the difference between dimension of homes from M to M, as I remember, as far as I remember, and dim of X from M to M.
Right. So it suffices to show that dimension of home MM is 1. So can you explain why? So just claim that if we are able to show that the dimension of the homomorphism space from an indecomposable to itself is 1, then we are done.
If Q is Dynkin, then this Q of dimension M should be more strictly more than 0. Then if we check that this is 1, then dimension of X should be 0.
Right. Yeah, because otherwise the value of the form is going to be negative. Yes, and then this would imply that Q of dim M is 1. Right, so the proof, is by induction on the sum of the dimensions of M, yes, Mi. So in particular, so the base of the induction, so if M is simple, so just means that it's one dimensional at some vertex and 0 dimensional to all other vertices, then it's clear. Obvious, yeah. Right, because I mean the homomorphisms from simple to itself is just the mapping, trivial, well, just map from one dimensional space to itself. Yeah. Now the induction step. So we just assume that for any L inside M, strictly inside M, subrepresentation, home LL is 1. Is 1 dimension. Then we have to conclude, we want to conclude that the same holds holds for M. And I'm not going to complete the proof. This is one of the problems in your homework. And so, well, please just complete it to make this step finished. Okay. So let us go back here. And so the goal was to show that the image of phi is a subset of the set of positive roots. And now we are done. And we now want to show that the map is injective and surjective. So we conclude that actually psi is a map from the set of indecomposable representations of M into the set of positive roots. So now our second goal is to prove that, let us show that psi is injective. So what does it mean? It means that, so we are to show that if M1 and M2 are two indecomposable representations, such that dimension of M1 equals to, maybe I write it, sorry. So maybe I write instead M1 and M2, I write M and N, okay? So not to mix with the spaces corresponding to the vertices. Dimension N, then M is isomorphic to N. Okay, so actually this is not completely obvious, yeah. So the claim is that for a Dynkin Quiver, two indecomposable representations, two different indecomposable representations cannot have equal dimensions. Okay, so how to show that?
I think it's also in our homework.
It is. I'll give you an idea, okay, and then you will complete the proof. So we consider, so let D be the dimension of M, and well, actually dimension of N. Then we consider so just recall. So recall the representation space ED. So this is the space of all representations of dimension D of our quiver. And then this the space ED contains GLD orbits of M and N. So we have to show that OM equals ON inside E. So of course, one has to use that both M and N are indecomposable. And this is again homework to complete the proof. Okay, so once again, the idea is that if you take two indecomposable representations of the same dimension, so these two representations, they define orbits in the corresponding representation space. So, well, in principle, there are many orbits there, but the claim is that if two representations are decomposable, then they have to coincide. Okay. So this would show the injectivity, and the last thing to show is the surjectivity. So we are left to show that psi from indecomposables of Q to psi plus is surjective. So for that, we need to construct an indecomposable M with dimension M being D for any root D from psi phi 2. Okay, so given a root, we have to show that there exists a representation, an indecomposable representation, whose dimension is exactly this D. Okay. So how do we proceed? So again, let ED be the representation space. Okay, and let us take M in, well, this is a Q module such that dimension of M is D. Maybe I put an N here, well, any M so far. So of course, this is going to be our indecomposable, but so far this any M dimension D and such that the orbit of this M is of the maximal possible dimension. Okay, so just take a top dimensional representation. So so we claim that M is indecomposable. So let's use here a remark. So just recall that what is the codimension of O of M? Do you remember? Inside ED. So we had the formula saying that the codimensional dimension of the orbit can be expressed in terms of M. So do you remember what was the formula?
It is dimension of X.
Yeah, this was the dimension of X1 MM. So actually, this was not that complicated. Well, but so the we just computed the action of the group. Yeah. So so we have to show that the maximal this X is minimal for indecomposable. So again, so there is a homework problem to complete the proof, but let us do the first step. So so assume that M is not indecomposable. So then M decomposes as a direct sum of several sub-representations. Well, you can decompose it into the direct sum of indecomposable representations. And so the first step is to consider M isomorphic to M1 plus M2, where M1 and M2 are indecomposable representations. Okay. So so let's work in this situation. In the general case, I mean, M isomorphic to M1 plus M2 plus MR is left as a whole one. Okay. But let's work out the situation where we have two indecomposable direct summands. So so let us compute X1, M1, M2. So I claim, so let us actually show more precisely. Let us show that X1, M1, M2 is 0. So can you explain why? So we want to show that there is no possible non-trivial extensions between M1 and M2, of course. So the order between M1 and M2 does not matter. Yes, so we could put M2 and M1. So, but the claim is that we can't have any extensions between direct summands of M.
We argued that X from M to M1 was 0, right?
Say it again.
We already argued that X1 of M to M was 0.
Yes, yes.
So M is M1 direct sum with M2. So when we write it out, we get that X1 of M to M is the same as.
But you see, so we've shown that X of MM is 0 for indecomposable M, right?
Mm-hmm.
But what is our logic? We want to show that M is indecomposable. Yes, so we take our representation space ED and we take the orbit, which is of maximal dimension. So far we don't know that M is indecomposable. This is our goal. And as you are absolutely right. So actually, the way how we want to show it is by showing that X1 is 0, yes, and well, this would give us the desired property, but so far we don't know that. So let's just try to find an argument. So assume that it's not 0. Then what does it mean? That the X group is non-zero, non-trivial.
We have non-split exact sequence.
Indeed. Assume the X1 is non-trivial. This is equivalent to having a, so we have split exact sequence of the form 0 to M2 to some E to M1 to 0. Okay, so what do we know about the dimension of E?
This sum of dimensions of
Absolutely. And we know that M, the one we started with, is the direct sum of M1 plus M2. So therefore, this is nothing but the dimension of M, right? So we have E and M. So two representations of the same dimension. So what we can say about, so then let us compare codimension of E and well, dimension of E. Sorry. Then what can we say about dimension of OE and dimension of OM? So these are both, they sit in ED. So what can we say about these two dimensions? So remember, this M is M1 plus M2. So we have two representations of the same dimension. One of them is the direct sum of two summons, two indecomposable summons, M1 and M2. And another is non-split exact, so middle term in the short sequence containing M1 and M2.
dimension of OE should be greater.
Yeah, so I'm not sure if you remember, but this was one of our results when we were studying the representation space, ED, and the action of the group. And then we proved that if you have a direct sum of two representations, or you have a non-split short exact sequence with the leftmost and rightmost terms being our summons, then the orbit of the non-trivial extension is the dimension is larger than the dimension of the trivial extension. Okay, but this is the contradiction. This contradicts the maximality of dimension of OM inside E. Okay, so you remember that our M was taken with the condition that the dimension of the orbit is maximal for, well, among all possible orbits. Okay, so we conclude, so this implies that X1, M1, M2, and X1, M2 is 1, M2 and 1 are both 0. Okay. These are our conditions. These are our implications. And now, well, we want to somehow get some contradiction. So I mean, we assumed that M is direct sum of two indecomposable representations, and let's recall that D is not an arbitrary vector. So what do we know about Q of D? So what was the logic? So what's the value of Q on D? So recall we've just started with, so we are proving the surjectivity of psi, yes? So the psi is surjective. So what was our D?
QID of D should be equal to 0 or 1.
But is it possible it is 0? So what is our quiver now we are working with?
So we have positive definite Q.
That's
so
right. Yes, our quiver is thinking, therefore our Q, small q, is positive definite. So D is a root, so this should be 1, right? Okay. So by definition, this is Q of dimension M. Or this is dimension of home MM minus dimension of X MM. Okay, so let's write this explicitly. So this is the dimension of home M1 plus dimension of home M2. Maybe I don't write this. So let me write this follows. So dimension home M1 plus M2, M1 plus M2, minus dimension of X M1 plus M2, M1 plus M2. So can you tell me what do we know about the dimension of this X space?
It is 0.
Why?
Because all of X of MI and MJ is equal to 0.
Right. So we know that X1 MI MJ is 0 because if I is non-J, this is proved above. And what happens if I is J?
For indecomposable, it should
Yeah.
be
Yeah,
0.
you're right. This follows from MI being indecomposable. So this is 0. Okay. And now what do we know about this home space? Dimension of this home M1 plus M2, M1 plus M2. So what do we know about this dimension?
This is at least sum of dimensions between M1 and M1, M2 and M2,
Yes.
which are at least 1. So
Right.
this is at least number of summands.
So this is at least 2, right? So our So the assumption M isomorphic to M1 plus M2 implies 1 being U of dimension of M is greater or equal than 2. So this is no good. So we conclude that M cannot be, so psi is a surjection, and hence bijection. So this is the proof of the Gabriel theorem, modulo couple of homeworks, exercises to be completed. Yes. So any questions about the theorem, about the proof? Okay, so if not, let me stop the screen sharing. Okay, and so before I stop the meeting, so let me ask you the following. So, well, the semester is coming to the end, and I wonder, when do you need to get your grades? So is there some concrete date, or we just this year, or so what's the situation? Probably it's different for Skoltech and for HSC, but I think for HSC it's just until the end of the year. But what about Skoltech? Do you know? You don't. Okay, so then probably it's also until the end of the year. So we'll have several more lectures, and then we'll have exam. So I think it will be also in the form homework problems, and then discussion with me at some point. Okay. So any further questions, remarks?
I'm just curious what will be the topic.
Say it again, please.
I'm just curious what will be the rest of the remaining of the year.
I'm sorry, I can't hear you.
Sorry, I'm curious what will be the topic for the rest of the year.
I see. So we have actually two topics, and I'm not sure we'll be able to cover both, but we'll try. So the first is algebraic. So this is kind of the discussion on. So the reason why quivers are that one of the reasons the quivers are that popular in the algebraic society is that any algebra can be represented as the path algebra of some quiver modulo some relations. So this is the quivers with the relations, and this is the realization of algebras, finite dimensional algebras. So maybe we'll touch on this, and also there is the geometric part about quiver varieties and quiver Grassmannians. So we'll try to touch on both, but we'll see how it works. So it's not enough to cover all details, but we'll try to discuss something.
I tried to have a look at Canvas, and in the calendar we have classes up to December the 12th. I don't know if you didn't appointed it, probably this means that someone else did, and then maybe he or she knows.
But I think we don't have to care about this.
Yeah. And like for my sake, we could also just continue into January or February to talk about macrothema variety.
But no. Anyway, so we have to finish this year, because so we have to have grades this year. This is important, and both for Skoltech and for HSC. So there's no option to continue next year, but we'll try to discuss this year what we can.
But we can get grades and then we can continue.
This might be possible. Yeah. Okay, then see you next week.
Okay, may I ask